The scientific revolution starts now.
This is the Science Joy Podcast.
Let us see in the dark. Obviously, us, like probably most of the people who have contacted you in the last few months, we found out about you through this press release, right? About this idea that perhaps some of the tensions in cosmology might be resolved by pushing the birthday of the universe back a little bit. Well, a lot of bit, I suppose. So yeah, that's how we ended up reaching out to you. And when we met with you earlier, you kind of opened a few cans of how you had adjusted your understanding of the timeline in order to accommodate some of these tensions. And maybe a good place to begin. That's right. I definitely want to talk about these things, but what I really want to know first is the guiding questions that have driven you to the point where you're even studying the universe and these huge questions, and how you got to the point that you were asking these. Have you always been a person who asked such enormous questions about our world, or was it something that happened to you? What was the story of coming to the place that you're at, and what drives you?
Actually, I was very much interested in cosmology from the very beginning. I would say after I did my degrees and I had a little bit free time to think about what I should be doing in future, I got very interested in cosmology and what the universe around us is. But I could not pursue it for many years because that's not the discipline I did my PhD in. So I did work whatever I got the job for, as many people do. And then, but even at that time, early time, I was thinking about some theories about the tired light, why the redshift is there, and could it be due to tired light? So that kind of thing was in my mind right at that point. But then for almost 40, 50 years, I didn't get a chance to work on that thing. So when I found time, means after essentially retiring from active involvement in my other research, I got this opportunity with the University of Ottawa to teach cosmology and astrophysics as an adjunct professor. And that gave me the chance to look again into cosmology. And that's where I started, essentially, you might say.
Man, that's so crazy, because that's exactly what's happening to me right now. I mean, I also did my PhD in basic elastic mechanics inside of a biophysical system, but I've very carefully fought my way into a very similar position. I also teach astrophysics, cosmology, astronomy as an adjunct professor at this university here. And it's interesting how you can actually make your way from one discipline into another one. Was that really difficult for you? Like, what were you studying, by the way, in your PhD?
PhD I did in solid state physics, condensed matter physics, what we call today.
And do you know why you didn't get into cosmology for your PhD, or was it just something you hadn't considered yet?
Oh, there was no cosmology where I did my PhD.
Really?
So you have to have a professor. Like here, even in Ottawa, where I'm teaching now, I'm the only one in whole Ottawa, capital of Canada, who does astrophysics or cosmology.
Wow.
And in the academic way. I mean, there may be hobbyists here, but really, not really. So if a student asks me when they are taking my course about it, and I tell them there's no graduate program here. There's no PhD for sure. I have a graduate student somehow. This was very interested in for doing master's, so I took him for that. But really, that was an exception rather than a rule. But not PhD. They said no, he cannot be enrolled in PhD, just master's. That's about it. And that's true, because they cannot count on an adjunct professor to guide PhD. I might disappear anytime, and then what happens? So there should be a proper program at the university to really take somebody seriously in a PhD program,
And is that just a reflection of how few cosmologists there are relative to, say, biologists or chemists?
Actually, this is a specialization. Here, photonics is a big thing, and solid state devices development is a big thing here. So Ottawa really specializes in those things, and they are doing very well. Other places in Canada, they have a lot of big cosmology program. Even James Webb telescope they have a stake in that. They have invested in that. So it is not that Canada is not interested in that. It just happened to be in Ottawa, the focus is not in this field. But there are many other places, including Victoria, Vancouver, McGill University in Montreal, and so many other places, University of Toronto. Perimeter Institute, for example, in Waterloo is a well-known world institution in this field. So there's a very good programs here. It's just not in Ottawa.
I mean, it's really inspiring to me that you found a way to publish and do research as an adjunct professor, because, that's certainly not expected of the job. And I'm curious your route to that. Did you make collaborations at other institutions, or did you just write things up and send them out?
And this paper is actually unique because it's a single author paper, the one about the Big Bang, right?
Yes, it is indeed a single author paper, because I have collaborated with other people. I have some paper published in this field. I had some postdocs visiting. Postdocs are allowed, by the way, because then there's no responsibility for the institution to grant a PhD or something, or award a PhD. So that is allowed. So I had two postdocs, in fact, in the past, and they worked with me. And we published few papers together, but they are slightly different. Their job was really to see that what I'm proposing is a evolving or variable constants theory. What is the fundamental, or what is the basis behind it? Can they find some reason that they should be varying? Or they could be varying. And if they are varying, why they are varying in interrelated way? So this is the thing, this is the very basic thing we have to understand. Because this is one of the questions people ask, You think they are varying, why they are varying? What is the physics behind it? So these are my people, they are from Brazil, two of them. One is from Brazil. One was originally from India, but he's at Imperial College now. So we work together to really explore what these things are,
All right, so I really want to talk about variable constants, fundamental constants, and tired light, and some of these solution sets. But do you think that for somebody who maybe hasn't seen the headlines and doesn't know much about the problems in cosmology, and essentially, I want to understand what your work was trying to address in the first place?
Okay, what I was working on this kind of thing for some time, the tired light concept as well as variable constant thing, and I published few papers in the past on that. But what really got me interested in doing somewhat more serious work, which I presented in this paper, is that the data which came out from James Webb telescope, and a lot of articles I read about the so-called impossible early galaxy problem, which was detected by Hubble telescope, but really it became really very well established by the James Webb Space Telescope. So this is where I looked into it, that what could explain it. Then I came across
Can you just
paper.
for people, just assume that people don't know what that is? They probably do, but maybe just tell them, what are these impossible early galaxies? What does that mean to people on the street?
What it means that the galaxies which were born at the beginning of the universe, essentially cosmic dawn, you might say, they appear to be as massive and as evolved as the galaxies which we see around us. So that shouldn't be, that was not predicted by various models which cosmologists or astrophysicists had created. So the
Were they
prediction,
expecting baby galaxies, or what were they
that's
expecting?
right. That's what they were expecting, were the baby galaxies or something. But here, babies are almost as grown up as the adults. So this is where the problem was, and that observation really created curiosity of a lot of people in this field. What is causing them? And then people were scurrying around trying to explain.
Listeners of the Demystify Sci podcast, have you checked out our Patreon? If you are casting about for ways to support the podcast, come over to patreon.com/demystifysci and sign up to give us a couple dollars a month. For just a few bucks, you get early access to both of the week's episodes, and you get to join our Sunday patron chat, which is one of my favorite things that has come out of this podcast. We get together once a week with listeners and figure out what the podcast is going to look like going forward, what everybody's been thinking about, and try to solve some of the deep mysteries of nature, sometimes that we haven't even had a chance to really encounter on the podcast. If you don't have any cash right now, that is totally fine. There are a million ways in which you can support the podcast. You can tell a friend, you can join our Facebook, Twitter, or Discord, you can leave a comment on YouTube, and you can get all of your friends' phones and subscribe them to the Demystify Sci podcast. In addition, we have one more thing that we're really super excited about right now, which is the upcoming conference on April 6th and 7th of 2024. Tickets will come on sale soon, but for right now, just mark your calendars for that first weekend in April in Austin, Texas. Lastly, if you are someone who has some kind of talent, if you are good at organizing conferences or graphic design or anything, really, if there's some way that you want to contribute to the podcast and you have a skill, reach out to us and see if maybe there's an overlap. We would love your help. We would love to have you as part of the group. In the meantime, enjoy the rest of our conversation with Rajendra Gupta and come on over to patreon.com/demystifysci.
If you find something which does not fit your existing model or prediction, you want to see what is wrong. Can we correct it? So that's what people were trying to do. And then I came across a paper which was using the so-called tired light theory to really explain the James Webb data or observations, which was very interesting. But the problem was that theory cannot explain some of the, you might say, cosmic dawn, cosmic noon observation, or you might say nearby observation to us. So this is where the problem arose, that, okay, the tired light theory can explain something, but it cannot explain other thing.
And you're talking about this, are you talking about the CMB?
Not the CMB.
Okay.
I'm talking about just the observations, James Webb observations, tired light could explain.
Yeah, but what are the things it couldn't explain? You said there was some local phenomena.
Couldn't explain is the supernovae type 1A observations of the redshift of the supernovae. They are standard candles. They are considered standard candles, and they are observed from very low redshift to fairly high redshift in the range of 2.3, 2.4, 2.5, up to that range. But there's nothing between 2.5 and up to when the James Webb comes, redshift, very high redshift. Supernovae are not observable. They are too dim to be observed in that range, although there are other devices, like quasars, for example. They are observed, but quasars are not standard candles, so you cannot really use them to understand these relations which exist between the distance and the redshift.
Okay, let's come back to that, because we need to understand tired light as an idea first, because you said that it was somebody else, and maybe you can tell us who, had used this idea of tired light to address the early galaxies, but hadn't been able to address the standard candles.
And let's specify that the idea of tired light, as far as I understand it, is that light, as it travels a long distance, accumulates a red hue because it's the gradual lengthening of the wavelength as it travels across space.
It's losing energy.
It's losing energy.
Yes, it is losing energy. And why? How is it losing energy? That is really not very clear, but it loses energy as it travels through the space, and the energy loss is proportional to its own energy and the distance traveled. So that leads to a formula which is different from the standard formula people use. But what happens in the limit of very small redshift, all the formula are the same. So this is why when we could only see galaxies, they are not too far, in the 1920s and 30s, at that time there were a lot of models proposed to explain that. But as we were able to see more distant objects, it was found that tired light doesn't really work. So that is when it was abandoned.
Now, guys like Fred Hoyle clung on to this tired light thing all the way up until almost 1990, from what I understand. I haven't made it through all of his work, but I've got a big, huge volume sitting on the desk over here that I pick at. But it seems like at least some little faction of physics was still trying to make this work for quite a while.
Yes, actually, this is true, because Fred Hoyle derogatorily called the expanding universe as a Big Bang, because it was not supposed to be taken as seriously at that point, but that's the word which is stuck with everybody, and they call it the Big Bang universe now, proudly so. But yes, you are right. He was, and there were so many explanations given to the observations which could not be directly explained by tired light theory, cosmic microwave background, and why tired light doesn't fit the supernovae data. There were so many factors which were brought in to make those explanations, but they somehow did not stick.
And so your proposal is making use of tired light, but doesn't stop there.
No, actually, my first thing when I found the tired light was able to fit the observed James Webb data, I thought maybe tired light, if I combine it with the standard model, we might be able to explain. And that is obviously what one would do. And it is, most of the time, it is not really, people don't think that way how it can be combined. They think always one or the other way. But one thing is very simple, if you see, because distance traveled by the light is the same, whether it is tired light scenario or it is the expanding universe scenario. Distance traveled is the same. So that can be taken into account when you build a model. And that means if it is done properly, you don't need additional parameters to fit the data. We still can work with the same number of parameters which the standard model had. And that's what I tried first. But somehow it did not fit the James Webb data. That's when I said, okay, let me go back to the covariant coupling constant model, which I was developing to explain certain other things, at that point. And that model itself was not quite satisfactory to me. So there was some tweaking had to be done in that. And tweaking was that when we construct the metric to be used to construct the Einstein equations, I don't know whether I'm going too much in
go
detail
for it. We'll ask you questions if we're not hanging on.
Yeah. So what we did that it is not only the constants which are varying, which in the case of when you are using a metric in general relativity, then you are talking about the speed of light in the metric, and in the Einstein equations, then you are using also gravitational constant on the right side. But here, yes, we find speed of light and gravitational constant has some correlation, all right. But how about distance? How do you measure the distance? Distance is measured with the speed of light in any theory of relativity. So that means that was missing in my earlier theories, that the distance was not explicitly included in that matrix to be dependent on this variation. So
In
when
other
we
words,
included,
there's an assumption that the speed of light is constant, therefore you can pull the distance out of it differentially.
all the distance are, whether it's constant or not, but distance have to be measured in the units of the speed of light to be consistent in the special theory of relativity or general theory of relativity or anything. They must be measured that way. But now in the metric, I had to also make sure not only the speed of light is varying, but also the distance is varying just the way the speed of light is varying. So when I included that, then whole situation changed. And things started fitting beautifully. For example, the supernova data, and I tried some other things as well, which I don't want to go into detail. But really, those things started fitting so well that I was encouraged to see, let me try to use this model combined with tired light and see what happens. And that's where the surprise came. The data fitted very well, but the bad thing was that the universe age was coming out too much. That was scary. So I tried to correct and check whether I made some mistakes and repeatedly why it is coming out so high and this and that. Of course, I knew it will come out high because part of the expansion of the universe or redshift is not only by expansion of the universe, but also by tired light. That means expansion is not as fast as it would be if expansion alone was causing the redshift. And normally you relate rate of expansion inversely to the age of the universe. So naturally, if it is not expanding as fast, that means age will increase. But age increased quite a bit more than would be expected from this change in the expansion rate. So this was quite a bit surprising, and this is why I was a little bit worried, quite a bit worried that how it would, and this is one of the reasons people don't like this kind of model, that it has extended the age so much. But extending age, as I said, it is 13.8 to 26.7 giga years or billion years. But it's not that only. The formation time of the galaxies, if you go to higher Z values, then you find higher redshift values, then you find these time for formation has increased by an order of magnitude, by almost a factor of 10 or more. So it is not twice as much time available for forming the galaxy. You have 10 times more time available to form the galaxy. So that was encouraging to me now. I said, okay, I have to publish this thing. That's why I decided. Otherwise, perhaps I would have discarded this paper.
It's interesting you said that people are unhappy about this, because I feel like you have had remarkable success in at least being taken seriously or respected by the astrophysical community. You know, there's an interesting one of the, let's say, the biggest podcast on Earth right now had a cosmologist on the show this last month, who we've had on the show before. It was Brian Keating. I don't know if you know Brian.
Yes, I had discussion with him.
Oh, cool. Yeah,
I have talked to him. Not talked to him. I have communicated to him, I should say, by email.
And maybe that's the answer to my question, or what I'm trying to understand is, because there's other people who have brought up let's say, problems with the Big Bang in the past, and they didn't, and one person in particular, a gentleman that I actually knew when I was in New York, he actually came and gave a lecture to my students, who's, excuse me, Eric Lerner, who was this gentleman. He was actually a
Yes,
journalist who wrote this book in the 80s or 90s.
I know him.
Yeah, you know him also.
Hmm.
But it was funny because on the Rogan podcast, this big podcast where Brian Keating was presenting this story, he was very generous towards you, and he wouldn't even mention Eric Lerner's name. And so there's something about the way that you're handling this that has sort of evaded the immune system of that knee-jerk response. I feel like I'm surprised that that you feel like people are unhappy.
Oh, yeah, I think, like you mentioned about Brian Keating's interview with Dr. Alison Kirkpatrick, perhaps, and that was the one, and she was concerned that there not whole lot of things have been done with this model before it became so much public knowledge or media sensation, you might say, in some way. And this is something I never expected, but I just, as you know, in any university, there are media relation people, and I happened to be in touch with them, or they were in touch with me, or whatever, and they sent me a form and fill out this form, what you have done, and see if there is something they want to talk to media about. And I did that, and they just wrote back to me the way they interpreted what I had written, and they had pretty good interpretation of what I had written. So I said, yeah, go ahead. And suddenly it became a wildfire or something, which I never expected. It was just like any other paper I have published. There's no much different. I have published a lot of paper in monthly notices of Royal Society. It's not the first one. And so I never expected that happen. Now, once that happens, then it becomes scary. That means now you have to show to the people that it is going to work with other things also, not just with the supernovae data and the James Webb, but what about others? So I am diligently working, and I'm my student, which only one student I have, graduate student, who is working on that. He's working on CMB, cosmic microwave background. The problem is, because it is not a simple change in the model which can be adapted in existing codes. You have to essentially write these codes, and they're very complex codes. So then only you can show. But what we can do simply, which I have done, and I have the paper ready now, I'm going to be sending it most likely by Monday or Tuesday, is that in the cosmic microwave background, what is cosmic microwave background? There's a feature called sound horizon, which is the perturbations or oscillations in the photon and matter, or photon and baryon fluid, which is sound wave propagates in that, and they keep propagating, that disturbance keep happening until there is this so-called atom formation. That means plasma is no longer there. The temperature, because of expansion, temperature of the universe falls below, say, 3000 Kelvin, and there's no more plasma. But the whatever was in the plasma, these oscillation, which is hot and cold points in that, they get frozen in the photons, which are being observed as cosmic microwave background. So that thing can be calculated very easily. The sound horizon can be calculated very easily. And then it is considered that these perturbations are observable today in the distribution of galaxies. If you analyze the 2-point correlation between the galaxies, then you can see that it still exists, and that is baryon acoustic oscillations, BAO. So these are also not difficult to calculate. So what I have done, I have calculated the sound horizon. I have calculated the baryon acoustic oscillations. Because what you are observing is when you observe in the universe, you don't observe the size of the physical size, you only observe the angular size. So I take the angular size, which Planck has already measured, Planck satellite has measured, and also some data is now available on the angular size of the baryonic acoustic oscillation in the near universe, low Z
Can you explain to
values.
people what the difference between true size and angular size is?
True size is the physical size. Physical size of an object, for example, if you see an object at a distance x, it will subtend an angle theta, for example. If you see the same object at twice that distance, then it will subtend an angle half of that. So that's the angular size. And for example, we can measure the angular size of moon, but we don't know what its size is. Size has to be determined by other methods, like parallax methods or whatever, these kind of things. Similarly, about the sun, we know the angular size. So whatever we measure is angular sizes. So now that means when people say this is the size, say for example, sound horizon is 135 kiloparsec. That's not the thing. What they say, if it is at that distance, then the angular angle we are measuring of this in the CMB anisotropies, that angle would correspond to this size. Now, if I say the distance is different, in my model, the different distance is different, so size will turn out to be different for the same angle.
Mm.
That's what it is. So similarly, when we go back and measure in the near universe these 2-point correlation, distance correlation of the galaxy, we are measuring again the angle. And from that, depending on the model, you derive the size.
And this is one of the great difficulties of astronomy and astrophysics, right? Which is being able to tell sizes and distances of things. And this is why we have things like standard candles. This is why we have calculations that are based on brightness that tell you how far away something should be. But if we don't understand something fundamental about light and the way that it behaves as it travels over long distances, then we're in a situation where we can't accurately assess the cosmic map, so to speak. Is that correct?
Now, that's yes, that's something very relevant. Yes, it is true. That it is very measuring distances are a big problem. And for example, one of the thing job James Webb had to really recheck the distance measurements of various objects and the Hubble tension which exists in between the supernovae observations and other observation and the CMB observation, the difference between the Hubble constant there, they thought it may be due to the measurement problems, but recently they found no, that is not really so, that tension still prevails. I have to see, I have, for example, using the model which I have proposed, whether it still has that tension or not, but I would not know that until I have a code which can really fit the complete CMB data, not just the sound horizon data, which I have done up to now, which is the very simple one to fit. But the complete shape of that spectrum is requires a pretty complex code.
Can you explain the Hubble tension to me?
Hubble tension is that the Hubble constant, if we measure in the near universe, which is with the redshift between, say, very low values, say 1, 0 to say even 4, 5, 6, then it gives a value between 72 to 75, or that range, in the units of kilometer per second per megaparsec. But if the same, when the same is determined for the cosmic microwave background, it turns out to be about 67 in the same units. So that difference people are not able to understand, and this is called the Hubble tension.
And what is the Hubble constant?
Hubble constant essentially relates the rate of expansion with the distance, you might say, of the object. In simple terms, it's a little bit more complex, but
And so, and if there's a tension between low redshift objects and high redshift objects, it suggests that we have a misunderstanding about the rate of expansion across the history of the universe?
or we don't understand the physics, how it evolves from the cosmic microwave background time, which is, by the way, that redshift is about in the range of about 1100 compared to the redshift of 4 or 5 or 6, or even James Webb. The best it can do is go to 20. James Webb, the redshift, it can go to around that range.
So the redshift of the CMB is 1100?
Yes.
Wow, okay.
It's extremely high.
It's very high.
Yeah, that's why, that means we are seeing the universe according to a standard model about 380,000 years after it was born. Whereas with the James Webb, the earliest galaxy which we have seen are about 380 or 300 million years. So you are talking a factor of 1,000 there. So this physics evolved or changed during that period? Yeah, perhaps most people believe it doesn't. And that's the way models are developed. But if physics did evolve during that period, then that will reflect why the Hubble constant or something else has changed.
What does it mean for physics to change? Because at least when we're learning physics from academic perspective, we're coming up through college, we're taught that there's these laws of the universe and they're immutable, and gravity is the same here as it is over there, and it's always been the same and it always will be the same. That's why they call them laws, I assume. But
yeah,
what does it mean for physics to change?
I would say, is physics, or some people might even say, don't talk that physics changing, it is certain things within the physics might be evolving or changing. But whatever it is, but the thing is this, as I said, if the constants can evolve, like the speed of light and gravitational constant and all that, what is the impact of those changes on the Hubble constant? Is just an example, but there could be more complex thing than that. And people there are a lot of work done even to talk in terms of the fine structure constant evolving or not evolving.
Are there more simple systems on Earth that you're aware of where constants change over time? Are there other simple physical systems, like say ones that we play with in the laboratory or something, where is there ever a case where constants evolve?
If the constant evolves, then they are not called constants. If you can measure their evolution, that means they are not constant. You have to find something else, and what is constant?
It would just be called a scaling factor or something.
That's right. Then you say, what is the scaling factor of that thing? So, and then what is the rate of scaling? And there may be a constant involved there. The rate of scaling itself may have a constant there. So constant is something which we measure with our best ability, and the time frame we have been around or can extrapolate, or we can go back by certain means and determine whether the constant were the same or not in the past. That's the best we can do. The problem is most people, or most of the work which has been done, is to see how a constant changes or not changes by keeping all the other constants fixed. For example, if people are trying to see gravitational constant changing or not, they will say, okay, let's try to see gravitational constant changing or not. Keep everything else fixed, because we can't have a lot of things varying. But the problem is, which I have shown in several of my papers, that if one constant is fixed, then you automatically fix all others because they are correlated. There is one function which determines the variation of all of them, not one function in the same. The exponent of that function is changing. Like one could be, say, its function is f, for example, and you say f function, in the case of a speed of light, it could be c equal to current speed of light times f dependent on time. Another one, for example, the Planck constant, it would vary as f square. Gravitational constant varies as f cube. Now, if f does not, if you say c doesn't vary, that means f is constant. If f is constant, automatically g is also constant. Gravitational constant is also constant. And also Planck constant is a constant. Now, this is the problem when you try to measure something assuming, and then when you go to the various equations which are involved in this measurement, then you will find they invariably involve multiple constants. And in many equations, I find they cancel each other.
It sounds like you picked out quite a puzzle for yourself to solve here.
Yes, but it is simpler than that, because when they are co-varying together, then you have only to worry about one constant in the function, how the function itself is evolving, because all the constants are evolving in terms of that function. So if you can find how that function evolves, you have determined the evolution of all the functions, all the constants.
So it's like a second order evaluation of the relationship between them. There's a rate at which they change, and that rate is constant, and so that becomes the new constant. And they become scaling, and the old constants become scaling parameters that just change as a factor of the new constant.
That's right. The constant the constant themselves are not related by this function. Only their variation is related.
Yeah.
This has to be kept in mind. So their variation is determined by one function with different exponents on that.
And so is part of the difficulty of doing this work figuring out the mathematical way to say this accurately? Or is the great difficulty of the work finding the patterns in the first place?
No, actually there is an energy conservation relation which I used to determine their relationship in the variation. And that is in a separate paper I have. And if you use that energy conservation, then the thing is this: if one energy changes, then other energies would have to also evolve. And you can take, for example, a star exploding. It has different kind of energies involved in there. Nuclear energy involved, you have gravitational energy involved, you have thermal energies involved, and all these things have, when you study them, then you find if you want a energy conservation in them, then they have to be, their variation has to be interrelated. I'm not saying that function is, this theory does not tell whether that function is evolving or not. that could itself be a constant. In that case, it's not varying. See, this is what it only says, that if they vary, they have to vary in a related way. They cannot be independently varying. But it doesn't say whether it varies or not.
So this variation we've been talking about is in the temporal domain, like the constants changed over time, right?
Yes.
Is there any way to separate out whether it's the temporal domain or whether the constants just vary with distance of travel path?
In cosmology, distance and time are the same.
Aha.
For example, how you measure distance? I say 20 light years. How much time it took to come here? 20 years. So they are essentially, you are using it depends what scale of measurement you take. If you are taking speed of light as a measuring scale, then yes, the distance, and it will evolve with distance or time. It's the same thing.
And then
or redshift.
Mm-hmm.
You might even say it revolves with redshift. It's the same thing.
That's so interesting. Yeah, that's a real knot to untangle by itself. Do you have any sense? Do you spend any time thinking about what would cause this change to occur mechanistically?
That is where I mentioned about the postdoc I had with me, and they are now professors at Brazilian University. They are working on it to find what could be the mechanism for such change. But we don't even know what is the mechanism of them being what they are, the constants.
In terms of just the underlying physical reality that gives rise to the constants?
Yes, yes. One means we can see why constants are what they are. Why speed of light, speed of light is, say, 3 times 10 to the power 10 centimeter per second is this value, why it is. Then some people might say, okay, go to the Maxwell's equation and you will find it is related to the permittivity of space and permeability of space. And you take the product of that, the square root of that, and invert it, and that becomes the speed of light. But why then permittivity of space and permeability of space is what they are? What is the reason for that?
Well, so figuring that out, I think, requires having a conversation about the nature of light and the nature of reality, right? Because something that we spend a lot of time thinking about, because we're writing this book right now about the nature of light and gravity and the emergence of relativity, is that our most complete mathematical theories of the universe are quantum field theories, where when you look at the nature of reality, you come to a mathematical conception of it. And a mathematical conception of reality seems to me to be a fantastic description, but it can't get at the question of why is it described this way? Why does it have this description? And it seems like thinking about a physical structure for space, a physical structure for light, became very unpopular right around the emergence of relativity, right around the early 1900s. For good reason, right? You can't detect the ether's not there. You come up with mathematics that mean that you don't have to deal with the ether, and you can just move on and you can work in mathematics. And so I wonder, do you think that it's possible to get at the question of why is the permittivity of space the way that it is? Why is the speed of light the way that it is, without starting to think of materials again and condensed matter and things like that?
I think it's a very good question, because it is quite philosophical as well. Because, for example, until we found existence of quarks, we were not sure why the various elements are what they are, what their constituents are, and why they have the structure what they have. But quarks and other particles, when we knew about other particles, I'm not particle physicist, so I won't go deep into that. But then we found, oh, there's a common denominator in all these things, whatever nuclei we are seeing. And we can construct it using these elementary particles, these nuclei. And there's an explanation for these rather than just creating a periodic table and saying that's the way they are. So I think same thing we might find that these constants, we are saying constant and independent constant might be related by something more basic, which we don't still understand.
Well, so Einstein, when he talked about when he talked about relativity and when he talked about space-time, would talk about this big tension between his non-physical mediator for gravity and what he called a non-kinematic ether, where he seemed to recognize that there had to be something that was down there that could be conceptualized as the mediator for all of these interactions. But it's almost like there's this fascinating parallel between Newton, who comes up with a theory of gravitation, a mathematical theorem that describes how things attract, but then ends his treatise with hypothesis non fingo when it comes to coming up with a mechanism for it, right? He's like, I have the math for you, but I cannot tell you why this happens. And it almost seems, and you read about the way that people interpret Einstein's work, and it seems like they interpret Einstein's work as a solution to Newton's lack of mechanism. Like, space-time is the answer to Newton's hypothesis non fingo. But then when you look at Einstein's own relationship to the work, he too is almost saying hypothesis non fingo, because he recognizes that he's invented a new mathematics for being able to describe it, and it's very effective, and yet he's still tortured by the question of what is actually down there. And we know now in a particle accelerator that you can hit empty space hard enough and have particles fall out of it. And so we're stuck with the same question that we had after Newton that we thought that Einstein had solved. And yet we're sitting here and we're looking at the landscape and realizing that, well, empty space isn't empty, and you can get stuff out of it. And so that must mean that something about the way that we conceptualize
material existence,
but even immaterial existence, like photons, right? Because the photons have to be somehow interacting with that empty space. And so if the space isn't empty, is there something that the photon is interacting with that is the mediator of its travel, which would give us tired light, which would give us a solid why for all of the things that we see, that you have found that are there?
This is, as you say, this is a very challenging thing to even discuss or talk about, because there are so many conjunctures people might have. It is very difficult to say we have a theory for these things. For example, just things in terms of the Higgs bosons. Now, we know that it has to be mediating particles when the interaction takes place. Now, photon, we know it is interaction between electron and proton or something of that, and it results as a result of that interaction. It is interaction. Photon is a something which really communicates this field between why these things two are interacting. Similarly, Higgs boson is considered the missing particle, why the many of the forces which exist in nature between particles, why they are there. So I think, to me, and in terms of nuclear physics, you will see the gluons coming in there. Gluons. So you have mediating particles there, but if you want to go to more basic things in this, I would say I don't have expertise to really talk in that in detail.
But when it comes to thinking about light and thinking about tired light, you're left with the same question of why. Why would the light lose energy traveling over long distances?
Yeah, I think this is one of the problems they faced. Zwicky, for example, in 1929, he has this problem, and they thought it could be interaction of the light with scattering happening with Compton type scattering with free electrons in the space, and they may be causing, but that couldn't be, because that will cause the objects to become blurred if that happens. But that was not the case. So the thing is this: what it causes is not known. But if we don't know the cause, it doesn't mean we should ignore the effect.
Of course.
So this is what I would say. I could say there are a lot of theories people are proposing, which is viscous fluid of the universe, the cosmic drag, so many kind of things people are talking. Any of these, it could be just cosmic drag of some form. For example, if the field a photon is passing through is not 100% conservative field, then it could be a lossy field, and it can, over very long distance, it might lose some of the energy. This is one of a simple, naive, again, I should emphasize, naive explanation, which most people will reject. That what is the mechanism? I don't know what the mechanism is.
I mean, one thing that just seems kind of obvious to me, I mean, my background's in elastic mechanics, and when I think about sound waves traveling in a material, like waves traveling in a material, say phonons or sound waves of some sort, the stiffness of the material, of the substrate, affects the travel speed. And I wonder if there's something at play. Obviously, completely naive once again, because we don't know anything about the tensile nature of the medium, or if there is a medium. Most people seem to think there isn't a medium. I did read a really cool paper by this gentleman, I can't remember his name, he was at Princeton, and he did, I think, 10 or 12 different deconstructions of if you were to model space-time as an elastic medium. He tried to reconstruct the stiffness of that material. And I'm not sure if he considered that it was variable, but he did pull out essentially the fact that it was unbelievably stiff, like some like 10 to the 100 newtons, you know, like an unimaginable elastic modulus. And when I think about how you would get something like a speed and to a constant speed to change, stiffness seems like the go-to answer for me.
To me, first I have to understand, again coming back, why the speed of light is what it is. What is limits it to time 10 to power 10 centimeter per second? Why it is not 5, or why it is not infinity? Is it because something is preventing it from moving faster than that? If something is preventing moving faster than that, you know the terminal velocity of a particle dropping in a fluid. Okay,
Sure, yeah.
so why the terminal velocity itself is, we know what is terminal velocity because viscosity itself doesn't allow it to go any faster, and you can determine the parameter of the fluid from
Basically, because
determining that
the
terminal
particles
velocity.
can't get out of the way fast enough, right? I mean, that's what it comes down to.
Exactly. So now here we are not talking about particle, but yeah, stiffness and all that. There's no ether or whatever medium there, but the fields are everywhere. If the fields are the one, are they all 100% conservative, that they cannot absorb any part of the energy or take any part of the energy? Maybe they are not. We are assuming it. If you put a little bit of that, and again, I'm not a person who can solve this problem. That's why it has to be handled by. This just conceptually, I'm saying that there could, if the speed of light is limited, and you can always explain it in terms of permeability and permittivity, but apart from that, you still have to see why it is what it is. If you can explain to me that, then I can explain why they are varying.
Yeah, I mean, it's going to be pretty difficult to do that if we don't have a mediator for these things. And you mentioned fields, and fields are okay, but they're a little unsatisfying because a field is a dynamic quantity, right? It's something that's changing with time. It has this dynamic component, and materials are obviously static. They don't vary with time. And so a field isn't really a material. It's a nice analogy or something, but it's still not quite the basement level understanding that we would hope for.
Yeah, this is where I think we have to find some new physics. That's why it is not explained. I can't explain. I'm just this is one of the things which I'm not capable or competent enough to really dig into and see why it is. All we see, could be the effect we measure, and how it happens, leave it to the expert to find out or not.
I think
we
it's
know
really
that
exciting.
effect exists.
I think that's one of the things that really excites me about science, and when I'm working with my students too, is always trying to find the places where discovery might take place 10, 20, 100 years from now. You know, what are the things, because it's very easy for students to get the feeling when they're just getting fed all of these equations and theories, it's very easy to get the feeling that everything's been done already. And so I think that these things aren't crises so much as just exciting opportunities for development. You know, this is where people can come in and really, really update our understanding of the universe in incredible ways. And of course, what you're doing is contributing to that massively.
Thank you.
You've written this paper. You have proposed that the universe is actually twice as old as it is. And you're working now...
Not quite twice as old.
Not quite twice, almost twice as old.
Almost, yeah.
And now you're working on making sure that the proposed model works in all of the various edge cases, because that's kind of the gold standard for how a scientific theory is moved into the starring role, so to speak. It has to solve a question, but it also has to work with everything else that was already solved beforehand. And so it's very challenging. And so this seems like it's going to take you a little while. But are there other things that you're also thinking about and also working on, even as you're trying to accomplish this almost unbelievably difficult task?
At the moment, I think my hands and mind is full with this task. So I don't think I have time to think something else. But as I had mentioned, I am working with some of my associates in trying to find a reason why they constant vary the way they do. So that is something I involved with. I cannot do that independently because that requires some different kind of expertise. Yes, I'm thinking about, but my main occupation is really to see whether this model is can work or what the deficiencies are, because a lot of models, they come and solve some problems but not rest of them, so they can't pass through. I am hopeful because the thing is this: I feel it is an extension of the existing model. So it is not that, for example, if I completely forget about the tired light model and forget about the James Webb data, there is a model, I still have that model that is able to explain the near-term observations very well. Now, people have objected about a model explaining the globular cluster or stellar ages, but this basic model, which you call covariant constant model, it doesn't involve extra age of the universe. It gives exactly the same age of the universe as the lambda CDM model gives. So there is no big challenge there. I'm pretty confident that that will work out pretty well. The problem comes when you have this extra age factor coming through the tired light. The tired light is the one which really complicates the matter.
And in order to really get people to accept this, I think that you're onto something with the trying to find a reason, right? Because tired light was dismissed over the course of the last 50 years or so as being a theory that wasn't the preferred version of things. And I feel like mechanism is always the most powerful motivating factor for bringing something back.
Yes. Okay. Let's try to go back to Newton's theory of light. What was that? Newton's theory of light was corpuscular theory of light. That it means the light travels as particles, and it was there for almost 100 years before people found that some of the diffraction patterns observed and the fringes they observed could not be explained by particles, and they brought the wave theory. The wave theory prevailed through the 19th century and some part of the 18th century, but come the time of photoelectric effects, which were observed, the emission of electron when the light shines on a surface, that was observed towards the end of the 19th century and early 20th century. Einstein resurrected the theory, particle theory of Newton to explain the photoelectric effect. So, and then eventually people found that all particles have the behavior of wave as well as particle. So photons are not only particle but also waves, and electron is not only particle but also wave. So I think this kind of resurrection of past old theories, which are more than 200 years old at that time when Einstein looked into again, it's nothing new. So I think I'm not so concerned about it. If it really explains the thing, then it is acceptable. If it just it explains one thing and nothing else, then it's just something in the passing.
Well, so the quantized model of light overlaps with Newton's corpuscular vision of light in the sense that you have what's a wave packet, right? You basically have this discrete unit of wave energy.
The quantum of action.
Is that actually?
No.
I like that. That sounds like a Bond title, the quantum of action. But so you have this quantum of action, and so the way that the corpuscular model is resurrected is not in a one-to-one relationship where it comes back to its little bullets of light. It's modified somehow. And so in context of that, do you think that your conception of tired light is different from the conception that was discarded somehow? Is it a modification, or is it the same as before and simply now brought to bear on a new body of evidence?
Yeah, there is, because as you said, the quantum nature of the photon or wave packet concept or whatever, this is where it is. But this is what was developed once Einstein said it is a particle. This can be explained by this method. Now, in the case of the tired light theory, I'm not saying the Compton scattering is really reducing its wavelength, or that is what is reducing its energy over multiple scattering process. I'm saying there's some unknown mechanism there's some kind of thing which has to be yet to be found. It could be some quantum gravity. Who knows? Whatever it is, I have no idea what it is. But there is, if
Stiffness of
this is what
space-time.
I'm saying, it's stiffness of space time. It may not be really there. Stiffness is still limit. Okay, 10 to the power 100. You might say, okay, it's such a high number. It is so stiff that nothing. It will pass without any degradation in its energy for 100 trillion years or something, or 10 to the power 100 years. But I'm not saying, there may be something more than that in there. I'm not sure what it is. But once, as I say, if we know and we can confirm this, there is an effect like this, then cause will be found.
Are you familiar with the... I'm sorry, I didn't mean to interrupt you.
No, go ahead.
I was just going to ask if you were familiar with the study of intrinsic redshifts in these active galactic nuclei. There's this gentleman, Halton Arp, who I think worked under Hubble, if I'm not mistaken. And he had a real firebrand of a career. He got himself in a lot of trouble with his peers. But he made a name for himself, and he published a book, I think it's called Seeing Red, where he's just got this catalog of galaxies where there are these jets that are pointed towards the observer, and yet they have high redshifts. And he's trying to make this case that there might be some other mechanism besides, let's say, Doppler or expansion that is responsible for redshift in some cases.
Yeah, I mean, we know redshift is the gravitational redshift is there. So we know there are so many other things which cause the redshift, but there could be some other effects which could cause redshift. But I'm saying, in this particular redshift which we are talking about, the tired light, I don't know any mechanism which can explain it at this stage. If what you are mentioning was explained by some basis, then it is fine. If it is not explained, then it is just another conjecture, I would say.
I think it was more just an observation. I'm not sure if anyone's followed up. Somebody in the comments will definitely tell us who's followed up on this work. But I think that now I'm going way back. I used to own this book like 10 years ago, but I believe that his explanation was that the creation of new matter in these galactic jets was somehow resulting in the production of redshifted light, something like that.
There was, yeah.
But I guess this is something else I want to talk about is, wouldn't it be nice if we could study cosmological redshift in a nice tabletop experiment in the laboratory? It's like, that's the one really frustrating thing about astronomy is all you have is light through a telescope, and you have to make sense of all of this history and all of these objects that are floating around in space. And it's sort of tragic that we don't have a way of interrogating redshift here on Earth in a way that we can just manipulate little things and try different solutions.
Actually, there have been a gravitational lensing, for example, of quasars and some other object. They might be able to reveal something like this, because gravitational lensing, when you are forming different images, they are traveling different distances. So that means the expansion part of the redshift remains the same. But because they are traveling different distances, that component could be different. The tired light component could be different. Unfortunately, it's so a small difference that it might be very difficult to observe, because the best you can do, most quasar images could be different by several months, maybe a year. But in a year, the redshift is so small that even if they are there, it will be very difficult to observe. But theoretically, yes, it is possible to really measure it. There are a couple of
I
other...
understand that. I understand it's measurable, but I'm just saying, like, in the sense of a laboratory experiment, right? This is still this is observation of these quasars, which are probably, how far away are we talking?
Oh, you are talking a redshift about 3 or 4 at least, so you are talking about
really far,
billions of light years away.
Billions of light years. Okay, my goodness.
They are very far away. But
right.
see, tabletop experiments means your sensitivity has to be extremely high. You have to get these accuracies of the order of 10 to the power 20 or better. Achieving 10 to the power minus 10 is itself is a big challenge for most of the things to do accurately. Now, trying to do atomic clocks experiments, yes, there's some possibility they might be able to get that kind of precision
Because they were able
for
to measure
doing
the
it.
gravitational shifts on Earth, right? Was it the Harvard Tower
Oh,
experiments?
yeah, that was relatively compared to the standards we have now. Mossbauer effect was used in that, isn't it? Mossbauer effect is extremely sensitive for these kind of things. So
Some sort
that
of
was,
phase shift, yeah.
yeah. So this is why I think there may be, but even if it is not tabletop experiments, even if it is a cosmological experiment, we might still be able to see. For this kind of experiment, I am suggesting the sensitivity will have to be much less than I mean than if we have to have a tabletop experiment. I'm not sure, but mind it. At one time, we didn't know how to measure the speed of light. But eventually, we will, with tabletop experiments these days, can measure the speed of light. So maybe it is possible to measure that eventually.
Yeah, I'm really curious if anyone's playing with that. If anybody listening knows of anybody working on tabletop exploration of redshift, I would love to hear about it.
One of the problem is first we have to understand that, okay, this kind of redshift, which is based on distance traveled,
Right.
is indeed a possibility. Once you have that, then you have to design an experiment in which you can detect this kind of thing. To me, I think designing that experiment and seeing all sorts of factors which might cause this kind of change in the wavelength of light, which will be, say, 1 part in 10 to the power 20 or something, it might be itself is a challenge. Just like, for example, gravitational waves detectors. Well, how much resources they had to put in there to really construct Lego experiments to be able to detect. And that too, even today, you can see they're measuring quite a few, but it is a task, a big task to extract the information from that noise itself is a big challenge. So I think if somebody says, yes, we have to detect this kind of thing and design an experiment, and people are convinced about it, if they are convinced about by some other means, and then there may be a possibility you design the experiment. But that's a good question you have. Maybe I should look into it and say what experiment might and what kind of accuracy will be required, what kind of sensitivity will be required to really measure it.
Yeah, I think that would be super valuable, just a short,
Yeah.
some sort of public discussion about that. I mean, I can imagine, I've never done anything like this, but I'm imagining some sort of phase shifting in a lot of mirrors to mimic travel distance and so forth. But when you're talking about hundreds of millions of light years, it's like you're going to be waiting around for a long time to stack up that distance. So it's tricky.
Yes. But see, the cosmological experiment, which I'm saying, that one itself, when you have a time difference of several months or a year itself, even then it might be a little bit tricky.
Yeah.
Here we are talking on ground. But if we can find there, then we might be encouraged to do the
I see.
experiment on Earth. But that is kind of thing which is a possibility,
Yeah, I think astronomy and astrophysics are very, very unique science because all we have is access to light. It's the only thing we have essentially. Of course, there are gravitational wave detectors, but still they're using light as the primary readout too, right? These laser chambers and so
Or
forth.
electromagnetic waves, not light only. Radio waves are giving huge information, sometimes even better
Yeah,
than
I
that
just
of the
include
light.
radio. I include all the
Yeah.
EMR in
X-rays
light.
and
Yeah.
all those, yeah, infrared, yeah, okay. Yeah.
But it's an interesting science in that realm because we don't have the same ability to pick at something. You know, in biology, we have all these different methods to touch the molecules. You know, you can use AFM to actually scan surfaces that are smaller than light, and you can use chemical reactions to get information, and you can actually probe the system. But astronomy is in this very unique position where you can't really interrogate the systems. You know, you can't poke at the stars or the quasars. Makes
That's
it
true.
very tricky.
Indeed, that's the biggest challenge with this thing is that. But the good thing is this, that in experiment we do here, we have limited, some other kind of limited data availability, okay, within the time frame we can do. In the case of universe, you have billions and trillions and stars and galaxies and cluster of galaxies that you can collect data from so many of these and use statistics, Bayesian analysis, and all those kind of things, which can provide you perhaps a lot of information which might be difficult to get here.
Yeah, you do have a lot of data, right? It's there's no shortage of data.
So much these days that human itself cannot do it. You have to have AI and machine learning and all these things to really analyze data. So I usually use the analyzed data. I don't use the original data, that requires huge resources to.
So you're using already things that have been processed already.
In some way or the other, but you have to make sure that most of the data we have is model dependent. If it is processed data, then it's model dependent. So I try to see which data is not model dependent.
Oh, nice.
And try to use that particular data. But it is very difficult to have completely independent data. For example, supernovae data. They are astrophysical type and cosmological corrections, standard model based or astrophysical model based. Astrophysical model will be more like how the supernovae emission peaks, at what time, there's peaking time, and that determines the standard candle parameters, So that is one of the things, but it's fairly complex. But that
so in other words, if it wasn't peaking when we thought it was peaking, then our use of it as a standard candle would be different. That's how it's model dependent.
Or the astrophysics itself. For example, there's the evolutionary nature of this in the cosmological sense. Then you will have a problem with that. Is
so
it really standard candle?
If at some distant time they were behaving differently and we weren't aware of that, then that would affect things.
For example, they involve Chandrasekhar mass. They all appears to reach Chandrasekhar mass when they explode. If they try to increase that mass more than that, then they explode. So that explosion involves Chandrasekhar mass. So if Chandrasekhar mass is itself evolving with the time, then that the luminosity of what we determine of these standard candles would itself change. And when that changes, then that means your distance will change.
And there have been some reports of contrary data points to the Chandrasekhar limit, from what I understand.
Yeah, there have been some, but at the moment, it is not confirmed because my model originally, my earlier model predicted that supernova Chandrasekhar mass changes. But when I included, and I was not very happy with that, but when I included the measurement of distance in terms of the speed of light in my metric for the general relativity equations, Einstein equation, then that thing disappeared. So now my model gives the same thing as the standard model or other astrophysical models. So they are still standard candles. So I don't have to make that correction.
It's so fascinating to me how there's so many moving pieces here. Like there's so many ways to attack solving a problem, because there's people working on these same tensions, right, from completely different angles, as far as I understand, by just trying to modify gravity or there's so many approaches to this, right? It seems like there's a lot of different parts of the fundamental understanding that if we shift them a little bit, maybe they would all be able to, I don't know, maybe we'd have lots of solutions on the table.
This is where, when you say laboratory experiments, we cannot do laboratory experiments. That's why we all can play with those unknowns. There are so many uncertainties and so many possibilities in cosmology. So at one point, cosmology was not even, or astrophysics was not even considered a proper science.
Of course, yeah. Yeah, cosmology just meant originally, and most philosophers still treat it this way, it just means the place of the humans with respect to the universe. It's kind of like who we are, really. It's not a scientific thing at all. I mean, in so much as that's not scientific. It isn't a hard physical science, let's say. Seems like it wasn't really until probably the 1960s or something with the CMB that it became a hard science.
Exactly. I think that's right. That's when people started to take it more seriously. Because at one time, they didn't want to give any kind of awards. Nobel Prize were not given in this field until way perhaps in 70s or later. And even CMB, first prize which was given was Penzias and Wilson for the CMB observation, which was he observed in 65 or something, and that was the first one. And Jim Peebles, who really predicted that kind of thing, or no, not predicted, he worked on that really to make it a science, really he got Nobel Prize in 2019 for the CMB, same kind of work, theoretical work. And theoretical was never considered seriously. And this is one of the reasons most of the things were in cosmology were theoretical. So nobody considered it any seriously for any important prize in those days.
Yeah, I just think it's really important and inspiring to remember how early we are into this science, right? We wouldn't expect that, 100 years into the invention of anesthesiology that we would have the best possible brain surgery worked out, right? We wouldn't expect that 100 years after discovering DNA that we would have everything figured out about genetics, right? So I think that there's so much more to this story that the future generations are going to put together. And it's really important for us to remember how early we are in our study of these cosmological ideas from a physical standpoint.
You are right, because other things you mentioned, they can be experimented on here in our labs.
Yeah, so they're going to go faster.
They can go a lot faster. Moore's law, for example, for semiconductors and memory chips and all processors. But really, this is a different kind of science. It has to cosmology and astrophysics depends on observations alone. So there are a lot of difficulties, and we try to get more and more powerful devices, and they're very expensive, and try to get the data from there. But but eventually, I think yes. But see, this is true in any field, because more you know, less you feel you know. So this is how much do we know about even a leaf you pick up from the ground? How much you know about it? We can't even make one cell out of it in the lab.
Yeah, I think that's really exciting, actually. I mean, nature seems to be. Have you heard of the concept of irreducible complexity? It's exactly what you're saying, that the more that we learn about something, the more questions that appear. It's almost like you dig down into the smaller or the very distant, and the less things seem to make sense than if we were to just get this surface level view where oh, okay, there's just gravity and stars and they're all pulling on each other and burning and so forth. And it's like, okay, that's understandable. But then we start to look at the little pieces of that big idea and the big picture starts to fall apart. It's very, very troublesome.
Well, that's why we end up, I think, with probabilistic stuff on the quantum level.
100%.
Right? Because it's too difficult to be able to map out all of the different interactions and all of the different ways in which they affect each other. And so it's much easier to say that this is probabilistic and we can use statistical mechanics in order to be able to say something conclusive than it is to dive down into each individual level. And I think that the same applies when you start to look at really big things, because the cosmos is vast and there's just so many edge cases and special conditions that you find rules that are general enough that you can apply them to your field of observation. And then there's outliers. Like that Halton Arp, one of his first books was the Atlas of Anomalous Galaxies. It was things that just didn't make any sense. And it wasn't that the outliers invalidated the bulk of the average. It was just that it underlines just how probabilistic things are, even at the large scale, where there are weird outliers that are probably representative of something that we don't yet understand. And we have a tendency of wanting to kind of sweep those away into the corners of the room because it feels satisfying to be able to say that we have a complete theory that works.
Mhm. See, I want to add one thing to it, that you said probabilistic thing, and if we knew everything about a particle and details, even for individual things in quantum mechanical system, we have shown probabilistic theory is still there, even on single particle theory. And that's the beauty of it. The uncertainty is there. Probabilities is there even for a single particle when you know things. Now you might say, if I knew everything about the interaction of everything, we might be able to still predict that. But this is what quantum mechanics said. You can't. There's not possibility. And that makes the whole thing very interesting. And this is why we say the universe is not mechanical system. It is, we came away from the mechanical kind of perception which we had before the quantum theory came into existence than what we have today. This is what I thought. If I didn't understand you correctly, please let me know.
I think that that's a useful correction. I just also wonder if our probabilistic interpretation of quantum mechanics doesn't come down to a lack of understanding about something. Exactly as you say, where if we can delve down deep enough and to understand the one level deeper.
The mechanics?
Yeah, the mechanics. Like I feel like we have a really,
like, I wish quantum mechanics was called quantum probability instead of quantum mechanics, because there's nothing mechanical about it. And I think that it gives, I guess that it worries me that there's like this tendency to believe that we have solved the mechanical issues because they just act differently or something, but it's not really a mechanical theory. And
I'm like, what if we had a mechanical theory, and what if the mechanical theory resolved this single molecule probability behavior? What if there's just something about the frame in which we're looking at it that gives us this mathematical outcome, but the mathematical outcome is predicated on a mechanism that we don't yet have?
tell them the genetic fields analogy. I always make Nastia came up with this beautiful way of explaining what she's talking about, and we've said it a few times on the show, but I think it's worth repeating because I think it's a really interesting way of framing what you're talking about.
Well, it helps me talk about it too. So, okay, imagine that we go back to before we discover that DNA is the hereditary molecule of the cell. And we know that heredity happens, right? Because we have Mendel with his peas, and we know that kids look like their parents and traits are heritable. But the people who are studying genetics happen to not be molecular biologists. They happen to be mathematical biologists. And so what they do is they study traits and they have many experiments and they come up with mathematical formulas that allow you to create a formulation of the genetic field that tells you with great probability what the next generation will look like. And so when we talk about genetics and heritability, in this universe, we talk about it only mathematically, only in terms of the way that the genetic field will probabilistically impact the heritability of traits.
And it's very accurate.
And it's very accurate. It's stunningly accurate. And you're able to predict what the next generation is going to look like really, really well because you have these great algorithms for determining it. I feel like in that world, we would have a lot of mathematical developments that are super useful for being able to create computer programs and for modeling things in nature. But what we would be missing is we would be missing the kind of molecular biochemical medicine that we depend upon in the world today, right? Like if you look at something like CRISPR-Cas, which is this tool that we can now use to modulate the genome of a living organism while it's still alive, that comes out of a biochemical approach to biology, which is we're going to take this protein, which is an object, and we're going to crystallize it. And after we crystallize it, we're going to figure out its structure. We're going to figure out how it works. We're going to figure out how to modify its active site because the active site has a shape that interacts with other shapes. And then we come up with this tool at the end of the day. But if we just have the genetic field, do we ever get to CRISPR-Cas? Do we ever get to, immune therapy? Do we ever get to targeted cancer treatments? I'm not sure. And that's kind of where I feel like physics is right now, where physics is in a place where we have spent a century mathematizing it to an unbelievable degree. We have mathematical equations that are precise to like the trillionth significant figure for constants. We have equations that let us do wild things, but we miss the mechanism. We miss the physical equivalent of the biochemical. And I wonder if that's not what the next frontier of physics is this rebirth of the old physics, because physics used to be obsessed with mediators. It's Michelson-Morley that killed the obsession with the mediator, and then Einstein saying, we don't need a mediator, I have math that lets it work. And I'm like, is there a future where the mediator is necessary to explain all of these things, to resolve the Hubble tension, to figure out tired light? Like, is that what we're missing? Maybe.
We have to redefine the mediator.
Yeah, absolutely, because the old one obviously doesn't work.
Yeah, that mediator doesn't work because the mediator itself, the way we were defining up to now, is perhaps very limiting. So unless we redefine that concept, we will be limiting in our scope.
Can you elaborate what you mean by the fact that it was very limited?
Limited in the sense that we are using the mediator the way we know, the way we historically know what mediator is. For example, what causes the gravitational attraction? Now, if you take the gravitational attraction the same way as the electron and proton attract each other, we have the photon as a mediator. What about gravity itself? How gravity, if you don't have general relativity, then how you need a speed of gravity to attract each other, objects? How does it? Yes, they are gravitational waves, I understand. But at one time, before general relativity was brought in, explain this gravitation, people were talking about what is the speed with which attraction takes place between different bodies. So they were looking for some mediator essentially. But then come Einstein, he said, no, it is the curvature of the universe. It's curvature which is created by the existence of that body. And that causes this thing, and there's no question of speed between these mediators. There's no mediator, essentially. That's what I was trying
Yeah, I
to
think
say.
it's going to come down to invest into imagining hypothetical architectures for the structures between those bodies. I mean, we have a good model for the atom, but we don't. And actually, we know that, for instance, the radial distribution function for the electron, we know that the atom extends to great distance. At least the electron can be found at almost any distance, although
Of
very
course.
rarely. We have a sense that there's something in between us and the sun. There's some rarefied something, but we don't understand its structure, and therefore we can't understand how it could possibly mediate anything. And so I wonder if the material scientists or people, how this will move forward in the future, maybe from outside of particle physics itself.
I think that what you spoke of earlier, which is searching for the why of the mathematics, is the future frontier of physics. Because I see a lot of people who really love the math for good reason, because it's kind of extraordinary. The machines that have been built to smash things together and to figure out these constants of the universe and to figure out all of the ways in which mathematically these things sum together.
It allows you to go to space, right? I mean, it's incredible. Airplanes, cell phones.
Yeah, I mean, like the technological advancements of the last 100 years, stunning. Like no question about it. But when it comes down to really understanding the fundamental nature of the universe, having a mathematical equation at the end of the day feels a little unsatisfying.
To me, mathematics should be considered a means of understanding something, not the end. And if we consider, many people say math is physics. If you can explain everything in mathematics, then that's what true physics is. To me, I think this is not the case. I believe that math is a means which to explain observations, whatever we have, and to connect all these things together. That's what math does.
Do you have a sense for when that changed in physics?
Could you paraphrase it differently?
Yeah, so I feel like there was a time in physics where mathematics was not the basement. It was not the basement layer. The general conception was much like what you're describing, which is that mathematics is a means to an end, not the end in and of itself. And then I feel like there was a shift where now we live in a world where the mathematics is seen more as the end rather than the means to the end. And so I wonder if you have insight for where that transition happened, because it's a very fascinating transition to me, because it's small at the end of the day, but I think quite significant.
It's foundational, though, at the moment.
Mm-hmm.
Yeah, my comment would be that really it is so easy to involve advanced mathematics when you don't understand physics. To convolute everything in a way that an ordinary person cannot perceive what it is. Mathematics was always used in physics. One way or the other, it was always used to explain and correlate the observation. Now it has become so complex, so difficult, that very few people many times understand what is going on. It takes you away totally from physics to explain something, and then to go back and really understand whether it is really the physics or just the math becomes a challenge. The models, that's why standard model is considered so good, because it's so simple. Why everybody uses it? Because it's so simple. Why Brand and decay theory and so many other gravitational theories are not really so popular? Because they are so complex mathematically, have become so complex that you don't understand that. So you don't understand where physics ends and where mathematics begins.
Yeah, I think that's kind of the tragic. That's the reason we even care about it, is because I feel like students who come into the fold and they want to understand how light and gravity work, they're very quickly confronted with mathematics, and it becomes this domain eventually where you whittle down the number of people who can even understand what's being talked about, to the point that there's a small room full of people who are telling everybody, well, and they're not even really agreeing with each other half the time, but they're trying to communicate to everybody else how these things work. And so if we limit ourselves to a purely mathematical conception of physics, then we run up against a wall where people aren't able to connect and people aren't able to understand who they are really in this material world and how things work. And I think that's a little bit tragic if we're not careful to at least find a place for those kind of questions to be asked. Because right now, if you try and go and work on a problem like this at a physics department, they'll say there's no funding for that, there's no place for that really. And likewise, if you go to the philosophy department and try to work on this, they'll say that's a physics problem. And so it's kind of an orphaned question set. And I think that it could be really valuable just on a purely social, physical, spiritual level, in terms of people being able to think about these problems. When you lose the mechanical side, when you lose the physical, it's very hard for lots of people to get involved.
This is why, one of the tasks of masters in physics, not master degree people, but people who know physics very well, is to communicate the physics behind the most complex mathematics. String theory, for example. I can think of Susskind, for example, taking simple lectures and explaining complex things in a very simple way. And many times, I personally feel that when I want to get into something more serious, I want to understand the physics of it first. And that's why I go to the simple lectures like those, to understand the physics before you go delve a little deeper into it. So I think there is why people say then you understand physics before we go into mathematics. I tell that all the time to students, my own students. My object is to bring out physics. Mathematics, once you know physics, you can work out mathematics. But if you know mathematics and you don't know the physics, then you will be just going in circles.
Yeah, and I think that's the worry, is that you end up with these untestable postulates where it's just like, maybe it's true, maybe it's not true. It's logical mathematically, but does it have any underpinning in physical reality? I don't know. And so I really appreciate that. I don't want to say I'm surprised to hear you say that, but generally mathematical physicists, people working on cosmology, wouldn't maybe approach it that way. And so that's pretty cool. I'd like to see more of that.
Thank you.
Yeah, do you feel like that's a unique perspective among your peers?
I don't think so. I don't think so. It's unique because I feel this is why I talked about Leonard Susskind. Why I say that his approach is understand the physics first. So many people who are really considered genius in that field are not because they have very advanced mathematics, because they understand physics about this. Jim Peeble, he developed his theories not because he had very strong mathematics. Yes, you have to be strong in mathematics too. This is true. It is not that you can do it without. But if you don't understand physics, then you are going to, yes, you can publish a lot of papers. That's not the thing. More complex mathematics you have, easier it is to publish the papers.
Mm-hmm.
It's not that. But and more data you plot, more analysis you do the data, you will be able to publish. But the thing is this, I come from very old school or whatever, but really for me, the way I was taught is you understand the physics first and then go further. Yes, some mathematics is required, but try to find physics first.
I love that.
Yeah, that's beautiful, because I think what you're getting at is kind of the strong versus weak link problem in science. It's like you can have all of these papers published, and they can just, maybe they'll get cited once or twice, right? It's not the volume that's important. It's really these ones that make a new understanding clear for people, that really integrate some solution set in an understandable fashion, because half of science is communicating it, whether it's communicating it to the journal, to your peers, or on a podcast like this. Half of being a scientist is not just having the revelation, it's being able to make that useful to people at the end of the day. And so that seems like a really healthy approach to me. I'm really glad to hear that from you. Do you have any closing thoughts? Is there anything you haven't shared that you really want to get out before we let you go?
Oh, that's a good question. I usually don't reserve anything at the as a closing thought, but I think what we talked in the last few minutes, to me, is something very, very crucial, and I want to communicate it to audience and future students or past student or whatever. Just whether it is physics or anything, have your concepts clear first. Whatever minimum tools are required for clearing the concept, yes, they are essential to understand. But don't think that if you have mastered a textbook or a specialized book that you can solve the problems. You have to have clear problem in your head and try to understand. Whenever you are going to delve deeper into something, don't lose the sight of physics about it. Otherwise, you will keep drowning yourself into it and never get anything out of it.
Yeah, that's beautiful. And I've heard that from some of my, outside of science, I hear this from people too. You know, I'm really into like rock climbing and music. And I hear this from some of the champions of all of these disciplines, is that, you know, they're not people who obsessed over the tools too much, right? One of the most famous rock climbers of all time, Alex Honnold, he's famous for, you know, people will come to him and say, okay, what's your training? What do you do to train? Do you do the hang boards and then you do a series of, you know, stepwise increase in difficulty bouldering and he's like, no, I just go and climb mountains. Like, that's what I do, is I want to be a climber, so I'm going to focus on climbing. And, you know, there's a quote from Jimmy Page. It's the same thing. And they're like, what's your practice regime? Like, do you play scales? And he's like, no, I just try to invent new ways of playing the guitar when I play the guitar. And so yeah, I really think there's something to that, where whatever discipline you're focused on, whatever your art happens to be, whether it's science or music or anything, you really have to have that vision for what you're trying to do at the end of the day, which in this case is physics. And so that's something you just can't lose sight of. And so, yeah, I really appreciate that insight. And I appreciate you giving us your time today. I know you must be swamped with all sorts of media inquiries. And so it really means a lot to me to have you come by and give us your time. And yeah,
thank you for giving me opportunity to be on your show. It has been really very good, and I enjoyed it very much because your questions were of the type which are I didn't have to explain in a words which I have to fight for. You know, finding them. Okay, what do I say? How, in what words should I explain this thing? Because I'm not really a good communicator to the lay people, although I have developed that skill now gradually. It's at a fairly low level after having so many interviews. But really, this kind of podcast which you have, that is not very common. This is not very different at the level which I give talks in a colloquium in the university. There is no dialogue, there is a monologue. Here we have dialogue, so that way it develops very well. So I really enjoyed it. Thank you very much for inviting me on your show.
That makes me very happy to hear that.
Yeah, it's fantastic. It was our pleasure.
Okay. All right. Well, have a great rest of your day, and good luck. I look forward to seeing what comes out. Maybe we'll meet up in a few years once you've worked a bit more on this problem, and we'll find out more.
Okay, sure. We'll be in touch. Thank you very much.
Right. Thank you so much.
Have a great rest of your day.
Bye-bye now.
Bye, everybody.
Bye.